Hey everybody, let's try not to wake him up. It's Mr. T back again with another one of my Time Out with T lesson tips on what was going on today. After our first day of online learning, I needed to kind of change up some stuff, and I figured, well, you know what, we need a little bit of some sunshine, some nice weather to get us through what's coming through the next couple days. There's a B. So I thought I'd figure, each time I do one of these lessons, Seymore and I, okay, so basically me, we'll try to pick a different location to film one of these, just to keep it different. Just realize all the stress that you're feeling, we're feeling the same on the teacher side of things, because lots of questions, very few answers. So anyway, let's start to have a little look at the neuromuscular system. I left you off with, can I do that? There we go. Perfect. I left you off yesterday with looking at the muscular system as a recap, and hopefully that wasn't too, wasn't too difficult. It's been a long time, so I can understand where it takes a little time. I'm still trying to figure out, with respects to what we were talking about yesterday, on, what muscles do I really want you to know. So I know there's a couple of you that sent me those emails. I will figure that out ASAP, but it won't be as much. So don't you worry, all right? So again, I left you off with this yesterday, and I think I passed through the slides, so I couldn't get a chance to really talk about it. But the 5 properties are key. The one we're going to really look at today is that the ability for the nervous system and a muscle fiber to conduct electricity. Electricity is the key to kind of how we control our movements and how we can, stimulate muscle contraction by sending signals from the brain primarily, but from some other areas in the body, to kind of elicit that response in our muscles itself. So, and then we got to think about on the, in the coming days, is that irritability factor with respect to when we send that signal, what's happening? Is the muscle responding? Right? Hopefully yesterday you gave a shout out with the reciprocal inhibition, and we'll talk about that a little later. So when we look at it, the neuromuscular system or neuromuscular junction is this midway point between the muscular system, those movers that you have, and then those controllers. So we have our nervous system controlling everything, telling the muscular system what to do. Now there is a whole other feedback loop to that, which we're not really going to get into, but it is kind of neat the way we establish this, feedback mechanism to create response, but yet looking at force production, speed, all these kinds of things on how we regulate that movement. And we control, we pull back, we go forward, we do all these kinds of things that we can. All right, so just kind of looking at it, we have to understand the neuromuscular system. There is a point to which we go from a chemical to an electrical, back to a chemical, and then back to an electrical. So there's always these checkpoints, and these checkpoints, if you think about it, are kind of important, because sometimes we get signals that get passed on that we don't really want them to go. And obviously this in certain situations can be really a detriment to your health, your safety, when your muscle goes to contract and you don't want it to, and there's these checks. And sometimes we lose that control. We can look at some kind of diseases out there where we lose the control to navigate or to control the signals that are being sent. All right. When we're looking at in the next 2 days, when we look at the neuromuscular junction, that specific spot where it goes from the electrical system to release a chemical that's then being received on the opposite side to create an electrical response. We call that the neuromuscular junction. And that point to which the two, that space, that chemical release is what we call, we jump the gap. We go from that presynaptic side to the synapse, which is the space, to that postsynaptic side to elicit some kind of response down the way. Catching this, Seymour? Sweet. All right. So what this really looks like, when we talk about a motor unit itself, we're really looking at the motor neuron itself. So a neuron is a nerve in its simplest form that's going to connect or control as part of a muscle, or a couple number of fibers per muscle. The axon, which is the part itself, and then the muscle fiber to innervate. So those 3 things really kind of make up your motor unit. What the heck is a motor neuron? So this is one of the things that has taken me a while to kind of grasp with how to better teach it, or how to better make you connect to it. And there's been so many analogies, and bear with me because I've got them all. And really one of these is going to stick with you for sure. So when we look at it first, these neurons are unidirectional. They go one way. They definitely, sorry, let me repeat that. They go one way in that they head from the nucleus, or what we call the dendrites, the receiving side of the axon, and they go down the axon to the axon terminal, which is the end of the axon. Now, in certain situations, we have multiple axons going, connecting to one another to get through there. And then we look at certain other ones, excuse me, that are extremely long because they need to travel long distances. So they're vary in size, but the shape and the consistency of what they're made of is really what makes them such a special cell and special collection of cells for its job. So starting on the accepting side, we have the dendrites. Those are basically the fingertips that reach out to contact other axon terminals to receive information from where it all originates from. Once this happens, they all collect into the neural cell body. The nucleus controls this and controls it and regulates it. And when it's ready to go, it travels down the axon and eventually gets down to the far side of the axon, and then it's going to cross over to what we call the terminal, axon terminal, or these little knobs, these terminal branches. And that's where those neurotransmitters, these chemicals that are ready to be released, are. Now, in order to get from the dendrites to the terminals, a lot has to happen. We're going to look briefly at that on how there's a sodium-potassium control that goes through it. But think of it this way. The axon is basically a tube, a nerve. Around that, you have certain things that help not only concentrate that charge, but also allow it to travel quickly. I think I need a sip from my Langstaff water bottle. So what's happening in all of this is when we understand that there's a covering around the axon, and we call this myelin. Myelin's really important because it insulates the axon and it prevents escape of the electrical charge as it travels down. Myelin is produced by something called Schwann or Schwann cells. You got to say it like that. You full send on this one. You got to go Schwann cells, because the Schwann cells themselves produce myelin that insulate the axon. Now, these myelinated sections aren't continuous throughout the entire axon. They have breaks, and these breaks have another great name, the nodes of Ranvier. No, the nodes of Ranvier, as they are named, are basically checkpoints between sections of myelin. And what really happens here is as the electrical charge travels down the axon from one node of Ranvier to the next, it goes extremely fast because myelin helps propagate the speed and makes it travel quicker through the axon. When it gets to each node of Ranvier, the message doesn't continue if it's not strong enough. So basically, it's a checkpoint to say, do we have enough of a charge to continue? Yes, go, fly, boom, to the next node, to the next node, to the next node. And this is how a nerve impulse travels along an axon from node of Ranvier to node of Ranvier. Now, that myelin is really important, and in coming up lessons, we're going to look at certain diseases like lateral sclerosis and multiple sclerosis, where we look at the breakdown of either the axon or that myelin sheath. And that's really important because if you have a signal going down the axon and it doesn't get to the end, something's missing. The response, the feedback, it could be a number of things, and that could be detrimental to not only your safety, but your health. And if that message is supposed to go to your heart to beat or your hands to move, as you can see, there is a huge response that's being missed here. So looking at just the terminals, or sorry, the names given to these, they're kind of straightforward. I've explained them right there. The axon is the path. The terminal is basically the start of the axon, where it connects to other fibers and other neurons to get messages. Think of this in your brain for my bio people, talking about when we look at neurotransmitters with respects to emotion and post-exercise, when we release serotonin and we release melatonin and we release a whole bunch of chemicals that regulate. And basically those chemicals are just going between in synapses across from a presynaptic to postsynaptic side. Then we have the nucleus, which is obviously the control center, your myelin sheath, which is the wrap around, and then the node of Ranvier, which are those gaps. Now, what I want to actually get back to is here. Okay, so here's my first analogy. Excuse me. Where'd the sun go? Okay, so my first analogy is one like this. If you think of if in your house or wherever you are living, if you have hot water pipes, you got a copper pipe. If you think of sometimes if it's a hot water pipe, to save electrical costs, you wrap the hot water pipe in a kind of a black foam, styrofoam or foam type wrap. That's kind of like the myelin is around the copper pipe, which is the axon. If you're a foodie, think of a hot dog in a bun. Imagine you had a whole chain of hot dogs that weren't disconnected. They still are tethered together, and you just put a bun on each hot dog. You have a perfect axon. And if I had my barbecue going, you know me, I probably would be doing this right now. My final one, which is a video that I linked in this lesson, is basically a subway station. If you think of Finch as our closest subway station, think of that as the kiss and ride, the bus drop off, all of these as dendrites. And we come into that main collecting area in Finch subway to get on a subway. So if we think of that, to get into the subway, we got to pay, of course. Think of that as the nucleus that controls us through. Then if you think of the subway itself is on the tracks. The tracks are the axon. All right, and that's the pathway we take. And if you follow that, the subway tunnel itself is the myelin. It allows us to travel through the tunnel on the axon and to go quickly, obviously, because if we had no tunnel, we wouldn't have any kind of movement. And then each stop along the way is a subway station. Those are your nodes of Ranvier. So let's say we want to go to a Raptors game. Well, let's think back. It was last year, 2019 finals. And you're getting on at Finch subway station. Your end stop is the Air Canada Centre. We're going to follow this example a little bit later on when we look at what happens in the Air Canada Centre with respects to being in the muscle. But let's imagine that the Air Canada Centre was a muscle. So we all get dropped off at the kiss and ride. We take the GO bus. We collect into Finch. We are now gone through the dendrites into the neural cell body. We get on the subway at Finch after paying, of course, and that's important because that's the nucleus. And it's not just a good deed, it's also kind of important in the story, being the nucleus is the center of control. We then go down into the subway, we get on the track in the subway, and we travel through the myelinated tube sections of the subway to the first stop, the next stop, and so forth. Once we get to the end station, for those of you that don't know, that would be Union Station, if we're going to the Air Canada Centre to see the Raptors game. Once we get out of out of Union at the subway stop, we have all these different types of stairs, escalators, all of these different ways to get out of Union Station. These are your axon terminals. Now, if you really know your stuff, you know that there's a hot dog vendor right outside the one stop. Think of that space between the Union Station where the hot dog vendor is, and usually a lot of pigeons, and the Air Canada Centre. That's that neural gap. That's a synaptic cleft to which you're going to go from Union Station through that open space, smelling the lovely street meat, and getting into your final destination, which is the Air Canada Centre. So if you can imagine that analogy, that might help you out with respects to what really a actual nerve and a propagation of neural impulse is down an axon. Okay, and I think more and more, if you have questions on that, please get back to me on that, because that's a really hard thing for some. But if you can kind of get that subway analogy down, you can understand it. Watch the video, a great King Cafe project by one of my students, 2016, and how they did it. Now, we have to understand, though, is the speed to which all this happens is really how we look at reaction time. And when we look at certain athletes in certain sports, we look at goaltenders that need to react. We look at football players, wide receivers, and defensive backs, and free safeties, all these positions that need to react quickly. It takes a whole bunch of things that happen, but one of the main things is that neural pathway. What is the conditions that are ready for that reaction to take place? So one of the big things, and we'll look at that throughout the course, is in motor learning, is understanding and basically being aware of situations that can happen. This is why we practice different situations, so we can kind of assess as a situation is evolving, which way it's going to go, so we can react better. However, when we look at reaction time itself, that's something that we can train to a certain point, but it's also really the relative speed to which that go signal happens from the brain, from feedback from the eyes, who knows what else, sound, down the entire pathway when eventually getting to your muscle, and for that contraction to happen. Okay, so that's why we look at reaction time. Now, if we think back in the old days, well, hold on, I'll get back to that. We'll talk about Ben Johnson in a second, because regardless of whatever else happened in his life, he has had one of the fastest reaction times. And I'll end our lesson with a proud Canadian moment for 9.79 seconds. Was how proud we really were. Last point I want to, though, is a motor unit itself. It kind of just doesn't kind of go. It's all or nothing. So when that signal gets sent from collected in the dendrites, and that nucleus passes the message, it's go time for all of the fibers that it innervates. Now, one of the important parts there, if you think of which muscles in your body do you need more control over? Okay, so think of muscles in your body, and I'll give you a comparison. Which do you have more control over, the muscles in your hands or the muscles in your legs? Let's say your quads versus your fingers. If you think that way, whichever you have more control over should have more axons connected to fewer fibers or fewer motor unit sections. That allows us better control. Some of us are very good. We're very good with our hands. We have good dexterity and movement. Some of us are all thumbs and we're very clumsy. That could be a relationship with how many neural pathways and axons are related to each one of those muscle groupings, and those that are better or more coordinated with their hands may be better off with respect to the number of that are connected, because it's all or nothing. Now we'll look at later on, when we look at strength and force production, how we recruit more. It's not that we're kind of creating a reaction in the muscle. It's how many fibers do we recruit to say, okay, we need more help, we need more help, we need more help, and therefore our force production goes up. Okay, so Ben Johnson himself. So if we look at Ben Johnson himself, take a moment, take 9.79 seconds to remember 1988 Seoul Olympics. His reaction time, one of the fastest ever recorded. We're going to get back to Ben Johnson in his 9.79 and that 1988 Seoul Olympic 100-meter final later in a unit we call ergogenic aids, and basically getting a little help from your friends. So I hope this helped you out. It's time for a little lunchtime and a little relaxation. Make sure you take care of yourself. Stay safe, wash your hands, and make sure, at the end of the day, we're in this together. All right, take care, and we'll see you later.